In this video, we're going to work through a duck simulator example. We'll start with a simple design and we'll add more and more features to our application. At each step of the way, we'll use design patterns that we've looked at in previous videos. This example is based on Chapter 12 of Head First Design Patterns. Okay. We're developing a duck simulator application for a team of very famous quackologists. These dedicated scientists are interested in studying the quacking behavior of ducks. So, we built a duck simulator for them with the following design. The duck simulator class contains quackable objects. Quackable objects must implement the method quack. Currently, there are 4 kinds of quackable objects in the application: mallard ducks, redhead ducks, duck calls, and rubber ducks. Our clients are very pleased with our progress, but in our next meeting with our quackologist clients, they tell us that they would like to add geese to the simulation and treat them just like ducks. It turns out that last year our group had worked on a goose simulator, so we already have a goose class, but it implemented a honk method instead of quack. The main question we have is, what design pattern can we use to add the goose class to our duck simulator? A related question is, how would the code have to change? And in particular, what existing code, if any, would need to be modified? Please take a moment to pause the video and see if you can answer these questions. Ready? The answer is, of course, the adapter pattern. So, let's move this goose over, and let's create our adapter, our wrapper class. The goose adapter class implements the quackable interface and has an instance variable of type goose. We implement the quack method by calling through to the goose's honk method. So we had to create a new class, but did we have to modify existing code in order to make this enhancement? Well, yes, we did. Not a major modification, but we still had to modify some code in the duck simulator. Code that is associated with creating our duck objects. Because now we have the possibility of creating a goose adapter object. Again, it's not a lot of code, but it helps to be aware of what you would need to do and what needs to be modified. Okay, so here's the simulator with the goose adapter. And the quackologists are quite pleased with what we were able to achieve. However, at our next meeting, they want to know if we can add the ability to count the number of quacks from individual ducks in the simulation. And of course we can. And we can use a design pattern to do it. But which one? And what code needs to be modified? And I will tell you that this one is a little bit tricky. Please pause the video and see if you can figure it out. Ready? The answer is the decorator pattern. Now, in the example we saw from Chapter 3, the decorator pattern was not used to add new methods to existing objects, but it can be. In this case, the decorator we create wraps a quackable object, and it also will maintain a private integer variable in its representation that keeps track of the number of times a duck quacks. When the method quack is called, it calls through to the quackable object's quack method, and it increments the quack count variable. As for modifications to existing code, it's similar to the last pattern. Code in the duck simulator that creates duck objects will have to be modified. This time, each new quackable that we want to count quacks for will have to be wrapped with the quack counter decorator. So now we have a duck simulator with a quack counting decorator. Again, our clients are happy, but at our next meeting, they want to make sure that each time a new duck is created, it has the quack counting ability. Well, we can do this by simply being diligent when we're creating new ducks. But it'll make our life easier if we use a design pattern to do this. And what design pattern do you think that is? Please pause the video again and figure it out. Ready? We're going to use the abstract factory pattern for this one. First, we will extract the code from the duck simulator class that is dedicated to creating ducks, and we'll move it to a factory class. In fact, we're going to have two factories. One factory will create ducks normally, and the other will wrap all new ducks in a quack counter decorator. Naturally, we had to extract and modify code in the duck simulator to do this. And actually, if we would have implemented the simple factory pattern before we added the goose adapter and the quack counter, it would have been easier to maintain the code during those enhancements. That's because we could have just modified the factory classes instead of modifying the duck simulator. Modifying the duck simulator class risked breaking other things. By the way, this diagram is leaving something out due to space constraints. I don't show the quack counter decorator, which is used by the counting duck factory. A more complete diagram would look something like this. Okay, so now we have a duck simulator with a normal duck factory and a counting duck factory. And our crazy quackologist clients are very happy. But there's just one more thing. Our quackologists want to be able to treat flocks of ducks just like a single duck. And what pattern do we go to for this? Please pause the video yet again and figure it out. Ready? Well, if you said composite pattern, you'd be correct. To implement it, we would need a composite class that we're going to call flock. The flock class implements quackable and also contains a list of other quackable objects. As with the other design patterns that added classes implementing quackable, we now have to modify the creation code of the duck simulator. But remember, we just encapsulated that creation code with the previous modification when we introduced the abstract factory pattern. So the duck simulator class does not have to be modified this time. Only the concrete factory classes need to be modified. Okay, as with the other changes, the quackologists are happy for about 10 minutes. So let's look at the final requirement from those crazy scientists. The quackologists want to be notified when any kind of duck, goose, or flock of ducks quack. Now, that word notified should be a key tip-off of what kind of design pattern you want to use here. So please pause the video one last time and figure out what design pattern is applicable here. Okay, Anytime one class needs to be notified of something that happens in another class, you should think observer pattern. The observer pattern has two main players. Number one, the observers, the objects that want to be notified when something of interest happens. And number two, the observables, the objects that the interesting things happen to, and the objects that have the responsibility of notifying the observers. Let's start with the observers. The observers here are the quackologists. So we will create a concrete quackologist class that implements an observer interface. The other class of objects are the observables. In this case, the observables are the quackable objects. So quackable objects should implement the methods that observable objects normally implement. For example, they should allow observers to register with them, and they should notify observers when something of interest happens. In this case, the interesting thing that happens is that they quack. Now the question is, where do we put the implementation of register and notify observers? One thing we can do is to put it in every concrete class. However, this would lead to a lot of duplicate code. In the book Head First Design Patterns, a helper class is created, and the concrete ducks simply call through to the helper code for registration and notification. In our case, we're going to put the code in the quackable class. To do that, we're going to have to change quackable from an interface to an abstract class. Once it's an abstract class, we can provide default implementations of register and notify observers. So, what code had to be modified here? Well, the duck simulator had to handle the new quackologist objects, and the quackable interface became an abstract class to implement the observable methods. So this is our duck simulator with the quack observers. Okay, now let's review the changes we made to our application and remind ourselves of the design patterns we used. First, we wanted to treat geese as quackables, so we used the adapter pattern to wrap geese and make them behave like ducks. Second, we wanted to count quacks, so we used the decorator pattern to add functionality to our quackable objects. Third, we wanted to make sure that the quack counter was added to each new duck, so we used an abstract factory pattern to allow us to create two different duck factories, one that did not add the quack counter and one that did. Then, we wanted to group quackables into flocks and families, so we used the composite pattern to allow us to do that. And finally, we wanted to be notified when any quackable quacked, so we used the observer pattern to help us implement that behavior. And here's the final design. Notice that the only pattern that forced us to modify existing quackable code, that is, code in the quackable hierarchy, was the observer pattern. The adapter, decorator, and composite patterns simply implemented the quackable interface. And that's it for this video on patterns of patterns. I hope you enjoyed it, and I hope you learned something about how and when to apply design patterns to your code. This is Dr. K. I'll see you in the next video.